Let's examine the effect of feedback on output impedance for an amplifier. Shown in the diagram here, we have a voltage type output amplifier. In other words, it's outputting voltage. And we've connected the standard voltage sampling setup to that amplifier. Notice that the beta network here is ideal in that the input resistance of the beta network is infinite. We've used kind of a hybrid model here, circuits on the right and block diagram on the left, because the inputs to this could be either voltage or current. We've denoted them with X. So the left-hand side here is block diagram, the right-hand side is circuit diagram. To measure the output resistance over here, we remove the load resistor and replace it with a voltage source. We also have to set XS equal to 0. So if we do that, we end up with this equation, which we can write for the output resistance. It's the output voltage divided by the current that would be going, through the output voltage test source that we put on here, value V out. So it's V out divided by I out, and this I out is really equal to, well, there's 0 going down this path right here, so it's equal to V out minus AXI divided by R out. And we replace that down here in the denominator of the equation. And then you realize that Xi, that's the Xi right here, is really equal to minus XF, minus because of the minus sign right there. And XF is equal to beta times V out. So we finally end up with this equation here. We can cancel out the V outs, and we end up with this nice equation right here. R out is divided by 1 plus beta A. In other words, R out is reduced by a factor of 1 plus beta A. And that is a really nice thing, because it makes the output resistance even better. For a voltage output kind of amplifier, you would want a 0 output resistance. So feedback really helped us out, and our little guy over here is just delighted. He's saying yes. Okay, now we have another amplifier here. This one is a current output amplifier, and it has an ideal feedback network as well, right here. It's a 0 input resistance. That's what you desire for something measuring a current. So what we want to do is we want to replace RL this time by a source of value minus I out. So you can kind of think we're putting a current that's going in the opposite direction here, minus I out. We're forcing a current in. We also want to set XS equal to 0. So when we do that, we end up with output resistance after feedback, which is V out divided by minus I out. And V out can be written as AXI minus I out times R out. And then we still have the minus I out on the denominator. And then we can substitute in for Xi as we did before. It's minus beta times I out. And then you can cancel out the I outs everywhere, and you get R out times 1 plus beta A, which is just absolutely delightful, because that's exactly what we want. And our little guy here is just absolutely delighted about that.